When it comes to the proton, the number of protons in the nucleus of an atom, it's also called the atomic number. Okay, so if I were to ask a definition about the atomic number, so the atomic number represents the number of protons in a nucleus. Later on, we will also talk about the atomic mass. So it is important to differentiate between these two terms, atomic number versus atomic mass. I'll show you an example from the periodic table shortly, and we can, we'll explain that more in details. Um, when it comes to the proton, the number of protons and therefore the atomic mass cannot really change without changing the element itself. So if you look across the periodic table, I'll show you here in a second. So this is an example of a periodic table. Actually has a lot of information, including color coding all those elements to represent either their metals, non-metals, and also to identify the specific blocks in the periodic table, the P block, the D block, and also the S block. But regardless of all this information, if you take any element from the periodic table, let's for example take the hydrogen up here. Okay, so we're talking about the hydrogen. So if you look at the hydrogen, there are two numbers on the hydrogen element or on the hydrogen symbol. There is number 1 on the top, and there is the number 1.0008. The number on the top here, this represents the atomic number or the number of protons. The number here on the bottom, this represents the atomic mass. So it is important to differentiate these two numbers. Okay, so this one is the atomic, this is the atomic number, and this one here, this is the atomic mass. Okay, so the atomic mass, because the electrons are in a constant move surrounding the nucleus in any atom, plus the electrons are very, very small, very small and tiny when it comes to their mass. They are not really factored in when we try to consider the mass of an atom. We only factor in the mass of the nucleus, where you have the protons and the neutrons. So the number for the atomic mass represents the number of protons as well as the numbers of neutrons. Okay, so it's protons plus neutrons. Okay, so if you were for example to look at something like lithium. Okay, so lithium that has 3 protons, correct, and has 6.94 when it comes to the atomic mass. So if you were to subtract 3 out of 6.94, you will be getting the number of neutrons. Number of neutrons equals, okay, let me just clear this one right in a better way. Okay, so the number of neutrons equals the atomic mass minus the number of protons. Or you can also say the atomic mass equals the number of protons plus the number of neutrons. Okay, so as you notice here, every time we increase by a value of 1 in the periodic table, going across from the left to left, or even going up and down, every time a number of proton increases by 1, you are basically changing the identity of the proton. Okay, I mean, excuse me, the number, you're changing the identity of the element. So lithium, for example, 3, if you increase by 1 proton, you will get beryllium. Okay, if you increase by 1, you'll get boron. If you increase by 1, which is 6, it's carbon, so on and so forth. That's why when we are talking about chemical interaction, number of protons are never involved. Number of protons never changes. Okay, because if you change the number of protons, you're changing the identity of the elements or the molecule that you're trying to react. Okay, in your reaction or in your equation. So that's why we never change the number of protons. The number that we change is the number of electrons, which are existing in the outer side of the nucleus, right, on the outside of the nucleus, circulating and just floating at a really high speed around the nucleus. So when it comes to the lithium, another term that I'd like to introduce here is the ions and the elemental form. So when you're talking about the lithium that has a 3 number of protons, and if you may remember, protons are the positively charged particles, correct? Because a lithium in its elemental state, so that means 3 protons, positively charged, must have 3 electrons, right, negatively charged. As a result, I have both of them cancel each other. So the total charge on the elemental form of lithium is a 0. Okay? So it doesn't have any, there is no charge associated with the lithium at this point. Not a positive charge, not a negative charge, but the number of protons, because the number of protons and electrons are equal to each other. Okay? So what information, to just sum up everything, what information can I get from the periodic table when I look at something like sodium? I can get the number of protons, which is, okay, number of protons, which is 11 protons. I can also get the number of electrons because it's at its elemental state, then number of electrons will be 11 as well. What do I get also? I can get also the number of neutrons. Okay, because as we said earlier, the number of neutrons will be the atomic mass, which is 22.9, and we subtract 11 out of that value. So it is going to be 11.9. This is the number of neutrons, but because neutrons does not exist in a fraction format, we say it's 12 neutrons. So we round that up, okay? Now the reason why it's always in fraction when it comes to the atomic mass, because the number that you see in the bottom of every element in the periodic table, it's the average atomic mass of that element, calculating all the isotopic formation of that specific element, because lithium has different isotopes, and we'll talk about isotopes in a second. And these isotopes mass are all calculated, and then the average is calculated from all these isotopes mass, and that's the number that you see on the periodic table being reported. Same thing for boron, carbon, so on and so forth. Okay, so these are the information that you can get from the periodic table. I would like you to pay attention to this. Okay, so back to the atomic number. So the atomic number, which is the number of proton, never changes. That is a solid fact that you should always keep that in mind. Because if the atomic number changes, the element identity will change because of the change of the number of protons. Okay, let's talk about the neutrons, which we just touched upon in a second ago. The sum of the numbers of protons and neutrons in the nucleus of an atom is called the atomic mass, and we talked about this because this is basically in the center of the atom, and the electrons is not going to be counted because they travel on a really high speed, plus the mass is very negligible. Okay, so atomic mass is protons plus neutrons. The mass number can vary of each element because the number of because of neutrons in the nucleus of an atom can vary. Same thing, if you look at the periodic table, you see the atomic mass are different from element to element because the number of neutrons will change. It's not the same. All right, let's talk about our friend, the electron. So the electron is that rebel guy in the atom, okay? So the electron, unlike the protons and neutrons sitting in the center, the electrons are actually the opposite. They like to be free. They always circulate around the atom. The nucleus, and the reason why we see it in this dusty sort of a cloud, and we can't really pinpoint for the electron, for two reasons. First, because the electron is super tiny and small in mass as well as shape, and second, the electron, they travel in an incredible speed. So, in order to really pinpoint where electron is, it requires really sophisticated techniques and really deep calculations, mathematical calculations. So that's why it is drawn as a cloud surrounding the nucleus, because it's a constant speed of traveling around the nucleus. I don't know if that makes any sense. Okay, so it's outside of the nucleus, generates a cloud of negative charge surrounding the nucleus, and that's due to the high speed of electron. And when the number of electrons equal the number of protons, atom is called uncharged atom, or we also call it elemental state. So something like a sodium, something like if you go back, oh, not this one. If you go back to unit 1. Okay, so if you go back to the periodic table, something like carbon, for example, the number of protons and electrons are equal, okay, because it's in its elemental state. So I have 6 electrons, 6 protons, the total charge is 0. Then it is considered an uncharged particle or uncharged atom. The negative charge is most intense at the nucleus and diminishes, and the intensity of the negative charge, it gets less and less as you get further away from the nucleus. The reason for that is because you have the positively charged particles in the nucleus attracts the electrons all the time and keeps the electron concentrated closer to the center. The farther away you go from the center, the less density of electron exists. Okay? And this has to do with a positive versus negative charge. Let's take carbon as an example from the periodic table. So carbon, and this is basically just another revision of what I just went through. So carbon has 6 protons, correct? It also has 6 neutrons in most carbon atom. And the reason why we say most, because the number of neutrons in carbon can vary due to carbon has different isotopes, and we will look at the isotopes shortly. And it also has 6 electrons. Why does it have 6 electrons and 6 protons equal? Same number. That's because it's uncharged atom, uncharged particles at its neutral state, okay? And it's also at elemental state. So that's why the protons and electrons are not the same. And I want you to keep that thought in mind for a second, because in a second we will be talking about ions, and we'll see how ions will form between protons and electrons, and we'll see how everything unfold. Okay? So in the center here we have the nucleus. The protons are the positively charged particles, so we always refer to them as positive 1. And the mass, as you see here, it's very small. It's 1.6726 times 10 to the power negative 24 grams. Okay? Neutrons the same. They're very small and tiny. Almost has the same mass as the protons. When it comes to the electrons are even much smaller. You can see 10 to the power negative 28, while the protons and neutrons are negative 24. So the electrons are even smaller in size. Okay, so the cloud represents the 6 electrons negatively charged that surrounds the nucleus in the carbon. So the mass number of carbon, it's 6 plus 6 protons plus 6 neutrons, and equals 12. Later on, we will see different mass number for carbon. There's carbon 12, there's carbon 13, for example. Okay, but because the protons are not gained and are not lost, please pay attention to this, because I don't want you to make a mistake in the exam. Protons are not gained and are not lost. Protons number remains the same. Neutrons, however, can't get knocked out from the nucleus. So you can lose or gain a neutron, which would make different mass for the carbon, which would result in isotopic formation of carbon. We'll get into this in a second. Before we get into isotopes, let's talk about ions. Ions, when the balance between the protons and electrons no longer exists. What does that mean? In a second, we looked, for example, at a sodium. Okay, so sodium has 11 protons in the periodic table, correct? If you look at the periodic table, the atomic number is 11. So it has 11 positively charged protons. And because it's at its elemental state, the 11 protons has 11 electrons to balance that negative charge, that positive charge. So the number of protons and electrons here is equal. When that balance no longer exists, that means I have less protons or more, less electrons or more electrons than protons. Then that's where the ion forms. Okay, so the number of protons will always remain the same. It never changes. The number of electrons, however, will change for sodium. So sodium can lose an electron, okay, and become an ion, a sodium ion, with 10 electrons. So in this case, I have a favorability of protons with one proton, with one extra proton compared to the 10 electrons, okay? So that makes the sodium, in this case, positively charged ion, or we also call it cation, okay? So I'm going to emphasize that one last time. Protons number never changes. The electrons that we gain or lose. I don't want anyone to write in the exam or in the homework, protons have been gained, or protons have been lost. Okay, so although the atoms of each element have a fixed number of protons, the number of electrons can vary, okay? Sometimes when elements form more complex substances, their atoms gain or lose electrons. So ions are more complex. The reason for that is because they exhibit different properties. They would have different tendencies and chemical characteristics that would allow them to involve in chemical reactions. Elemental and uncharged particles rarely get into any chemical reactions, okay, due to their inactivity. So ions are charged particles due to loss or gain of electron. Again, gain or loss of electron, not a proton. When particles lose, or when an element loses an electron, then you will have a positive charge, leaving them with a positive overall charge. They become a cation. So I have more protons than electrons, then it becomes a cation. Vice versa. If I have more negatively charged, overall negative charge, more, it becomes an anion. So that means it gained an electron. So every time it gained an electron, every time it gains electron, it becomes a negatively charged particle. Every time it loses an electron, it becomes a positively charged particle. And some people confuses this because they associate gain with positive and they associate loss with negative, and it's actually the opposite. So keep that in mind. All right, let's move on. Monoatomic ions. So because we're talking about ions, there are different kind of ions. There is the monoatomic and there is the polyatomic ions. I don't think we'll get to the polyatomic ions in this chapter, but we will, I think, in chapters to come. So a mono, that means it's a single, right? Mono means a single atomic ions. That means it's an ion with a single atom, not two or three, just one single atom. Example for that could be any element for the periodic table, like a sodium, magnesium, potassium, nitrogen, oxygen, all these folks. It's considered a monoatomic ion because it has only one atom. Uncharged, when it's uncharged, as you well see here, there's two negatively charged particles. Okay, let's color code things. So there's two negatively charged particles and there's two positively charged particles. Okay, so the positive cancel out the negative. That's why it's considered an uncharged atom. When it comes to the cation, the positively charged, you can see there is an additional positively charged particle, one additional, and there is one negatively charged particle. So there's two versus one. So this makes it positive one charged particle. When it comes to this one, as you see, the number of proton never changes. It's the same. It's always two, but we gained, however, 3 electrons. So this makes it 2 cancel 2. So then this makes it -1, or it makes it an anion. Okay, with one negative charge, negatively charged anion. Okay. Okay. Let's look at take an example from the periodic table. So if we take this sodium, for instance, as an uncharged atom, for the sodium, you have 11 protons, right? And you have 11 electrons. This is my atomic number. Remember, this is my atomic number right here. So I have 11 protons and 11 electrons. Now, when sodium becomes a positively charged particle, or also a cation, that means it is going to lose an electron. So when it loses an electron, it becomes a positive. There's 11 positively charged particles of protons in the nucleus. But before getting into losing an electron, let's clear this one. So we're talking about the elemental sodium. There's 11 positively charged protons in the nucleus, and there's 11 electrons surrounding the nucleus. When it loses an electron, again, it becomes 11 positively charged particles, or also protons, with 11 electrons. So I have an additional proton in this case, positively charged. So that makes the sodium a cation with a single positive charge. Okay, so the way we write this, it will be a sodium positively charged. Okay, let me clear this one. So it's a sodium positively charged. Okay, so that makes it a cation. Just like how I have cations, I have also anions. That means atoms in the periodic table that it never gains an electrons. It always it never loses an electron. It always gains an electron. So when you look at the periodic table, there are elements that loses electrons all the time, and there are elements who actually gain electron all the time. They never lose their electron, and we will explain that I think in a couple chapters, and why certain elements they always exist in a cation formation while others exist in an ionic formation. Okay, but at this point, I would like to know that sodium always loses an electron, never gains an electron. Oxygen, on the other hand, always gains electron, never loses electron, rarely loses electron at all. Okay. So when it comes to the uncharged oxygen atom, it has 8 protons, right? And it has 8 electrons. So it has always 8 electrons, 8 protons. They both cancel out, so I have 0 charged on the elemental oxygen. Oxygen always gains 2 electrons. So when it gains 2 electrons, then I will have an additional 2 negatively charged particles, aka electrons. And the protons number count will remain the same. So I have 2 negatively charged electrons more. So that would make it oxygen -2. And that's the oxidation number for oxygen all the time. We'll get into oxidation numbers later. Okay, but you get the idea. Cations and anions, and how both forms. So let's do some quick examples, and yes, I will. You'll see this in the practice problems as well as the exam, of course. So identify each of the following as cations or anions. So the nitrogen atom has 7 protons and 10 electrons. How do I find out if it is a cation or anion? As simple as just subtracting the number of protons from the number of electrons. So if you subtract 7 from 10, then you will get -3. Okay, or you can just simply look at this one. So it looks like I have 10 electrons, 7 protons. 7 of the electrons will cancel out the 7 of the protons, and then I'll have 3 additional electrons circulating around the atom. That makes it -3. Gold, 79 and 78. Same thing. If you do the same concept, you will have a positively charged gold or cation with 1 positive charge. Magnesium, same concept. So if you subtract 12 if you subtract 12 from -10, you will get 2 positively charged protons in excess. Okay, so that makes it a magnesium cation. Fluorine will have 1 negatively charged electron in excess, so that makes it a fluorine anion. So you subtract the number of electrons from the number of proton, and then you will know if it is a cation or anion. Okay, so that's in terms of cations and anions. Let's talk about isotopes. And isotopes are different than ion. So isotopes, although all atoms of a specific element has a fixed number of protons, just like how we discussed earlier, they may have different number of neutrons. So just like how our electrons are gained and lost, neutrons, under some intensive chemical conditions, you can actually gain or lose neutrons. And when you change the number of neutrons, you change the atomic mass of the element. As a result, it becomes a different isotope. So when the element has 2 or more species of atoms, each with the same number of protons, so our number of protons still remains unchanged, okay? But it has a different number of protons, then we call that one an isotope. So if you were to draw a comparison between ions and isotope, it's right there. Ions are formed when electrons are gained and lost. Isotopes, however, when neutrons are gains or lost. Okay, gained or lost. Isotopes are atoms with the same atomic number, but it has a different mass number. What does that mean? So I'm going to go back to the periodic table. So it has the same atomic mass. Talking about carbon in a second. Same atomic number, but different atomic mass. So the number below will change, resulting in a different isotope. The atomic number remains the same. Okay. So isotopes are atoms with the same number of protons and electrons in the uncharged atom, but different numbers of neutrons. So we're changing the number of neutrons. Fun fact, only 9 of the elements found in nature have only one naturally occurring form, but the rest elements are always composed from more than one different isotope. Okay, something like carbon, it has many different isotopes, 2 or 3. Uranium, for example, has also many different isotopes, and so on and so forth. All right, let's look at hydrogen, for example. So hydrogen, isotopes of hydrogen, which we also call it deuterium. Hydrogen atoms have 1 electron and 1 proton. Okay, looking at the periodic table. Different isotopes have different numbers of neutrons. Okay, so another neutron is being added to the nucleus, so that makes it 2 neutrons and 1 proton. Proton number remains the same. At this point, since the protons is still the same, it's still considered a hydrogen atom. However, it is considered an isotope of the hydrogen atom, and they call it deuterium. So a negative charge cloud still surrounds 1 electron of each hydrogen atom. That never changed. It's just the number of neutrons. Okay. For example, so this is the only isotope that it's known for hydrogen, deuterium. And this is widely used actually in chemistry and in chemical analysis and chemical studies. But when it comes to tin, for instance, it has many different isotopes, as you well see here. Okay, so tin 120, for instance, represents about 32.59 of when it comes to the tin existence in nature. Okay, and you can see how many isotopes of tin do exist naturally. So the atomic symbol for tin is Sn. The atomic number is 50, so it has 50 protons and it has 70 neutrons. Okay, and this is the total how much you have inside the nucleus. Now you see every time you change a neutron count, you are getting a different isotope of tin, and you can see how many 10 isotopes. Okay, so sometimes these isotopes have has a shelf life. Okay, so it decays. Sometimes it decays naturally. What I mean by that, it decays naturally. That means it loses neutrons naturally over time. And specifically for carbon, it really helps to study sometimes how old certain fossils are, because for carbon, for example, in order to convert from carbon 12 to carbon 13 or to carbon 11, it has they can really tell from the half-life of the isotope how long this carbon have been around. So it also helps to study fossils, and to study what happens to what happened to the universe, for example, by studying the half-life of carbon and see how long this certain fossil, for instance, has been around. Okay, so the decay process can happen either naturally or it can happen synthetically in a chemical reaction. When it comes to elements in nature, most elements are not found in a single atoms in nature. Okay, rarely found in a single atom. Elements are found as groups of atoms sticking all together, and the nature of these combinations depends on the particular element. Okay, so it depends. So the nature of these combinations, it means the type of bonding and how these atoms are interacting with each other. It depends on the nature of that element. What does nature of that element mean? It means it varies if it is a metal, it varies if it is a non-metal, it varies if it is from group 1 or group 2, so on and so forth. In nature, the structure of the atoms for each element is referred to as its elemental form. Okay? The structure of elements, when it comes to the noble gases, they always exist in a single atom. So the noble gases, if you have forgotten, this is the last column of the periodic table right here. Okay, so these are the noble gases. They always exist as single atoms. So there's a helium gas, the neon, and they always exist in a gaseous form as well. So on top of being gas, they also exist in as a single atom and not as a diatomic, not as a diatomic molecule. Okay, other nonmetals such as other nonmetals exist as molecules. That means it's more than one atom. So every time we say molecule, that means it's more than one atom bonded together. Example for that one, all the gases in the periodic table, with the exception to the nobles, of course, like the hydrogen, the nitrogen, the oxygen, fluorine, chlorine, and the halogens. So when we are talking about the halogens are the group adjacent to the noble gases right here. So all those folks, the fluorine, the chlorine, they always exist in a diatomic format. And remember, as we said earlier, a few slides ago, as long as they belong to the same group, they exhibit the same chemical properties. So if fluorine exists as a diatomic molecule, guess what? Chlorine, bromine, and iodine will exist in the same format. Okay, so oxygen, nitrogen also exist as a diatomic molecule, not as single atomic, not as a monoatomic, or in its as a single atom. Okay. Sometimes something like sulfur, if you look at sulfur right here, so sulfur can exist almost in a polymer shape with so many bonds, with so many atoms bonded together. So it can be sulfur 8, S8. Okay, just like with O2, there is an S8. Selenium, the same thing. It can exist with many atoms bonded together. Phosphorus is the same thing. Okay, so it can exist in a tetra format. So phosphorus, for instance, it's a atomic molecule. This one is a diatomic molecule. Metallic elements, cations, with really a big amount of electrons that surrounds these elements, or a sea of electrons. The states of the elements of the periodic table, it really depends if it is a metal or non-metal. But let's take some examples. When it comes to gases, obviously we all know that oxygen is a gas, nitrogen is a gas, hydrogen, fluorine, chlorine, and you can also assume that iodine and other stuff. Well, fluorine, chlorine, iodine is not really covered with this. Helium, neon, argon, krypton, and xenon, they also exist in a gaseous form. Liquid, bromine, and mercury also exist in a liquid form. Everything else is in a solid formation found. Okay. So mercury, it is really an exception, even though it is a metal, but exists in a liquid form. And I don't know if you ever used a mercury-based thermometer. Obviously, mercury, it is in a liquid form when you see it in the thermometer. Okay. The noble gases, the reason why it's called the noble gases, because they carry on a very low reactivity and they are rarely involved in any chemical reactions. Some recent chemistry has been investigating and has been exploring using noble gases in certain reactions. Certainly helium, neon, krypton, they have very low reactivity. Xenon, some chemistry, as I said earlier, has been shown some promising with xenon, but beside that, they are very inactive. So that's why it's called the noble gases. It is a single atom, 2 protons when it comes to the helium, 2 protons, 2 neutrons. It has 2 protons, 2 electrons, as I said. That's why it's an uncharged particle. So you will never find, when I say they have a really low reactivity, that means you'll never find a helium cation or a helium anion. You'll never find a neon cation or a neon anion, so on and so forth. They always exist in their uncharged format. Okay. Examples of other non-metal gases like the hydrogen. Okay, so the hydrogen exists as a atomic molecule. And again, when we say di, that means it's a 2. So we have 2 hydrogen nucleus to the on the side, and you have the bond, and you have the electron shared in the center. We will get a ton of more information when it comes to the bond formation and what kind of bond we have in hydrogen in this case, but I just want you to get this idea that electrons are centered between the 2 new nucleus of the hydrogen atoms. The space-filling model emphasizes the individual atoms like this one, and the ball and stick model emphasizes the bond. Okay, you might find them in 2 different ways. This model, basically, it can also be applied to oxygen, nitrogen, all the symmetrical diatomic molecule. And we say symmetrical, that means you have hydrogen on both sides, you have oxygen on both sides, and they are not. You don't have two different atoms. Okay, so they're both the same. Example of hydrogen gas. Obviously, this is where it's located in the periodic table. It's considered a nonmetal. Each particle is a diatomic molecule. Okay, and because it's a gas, they are far apart from each other. Okay, as we talked about gases earlier. Example of a nonmetal liquid, that would be a bromine. Okay, and bromine exists as a. I'm sorry, this should be a Br2. Should be a Br2. Okay, so bromine, because it exists in a liquid state, as we talked about liquid and solids and gases before, they are more closer packed to each other compared to the hydrogen, less space around, correct? So they keep bumping into each other. However, there's still a big degree of freedom for bromine. Okay, and it's still, and a bromine also considered a diatomic molecule because we have 2 bromine bonded together. Okay. So non-metal solid, we'll take iodine as an example. And obviously iodine is a diatomic molecule, correct? Because we see a 2 as a subscript right here. So it is a diatomic molecule. So it means we have 2 iodine atoms connected and bonded together. And this, you can see it here with this dumbbell model. Okay, so it also exists as a solid material in sheets. That's why if you look at iodine sitting in a jar, will have this type of like a pellet structure. Okay, because that's the way it is. The bond basically is formed, and that's the way it exists as solid material. Iodine, because it is a solid material, it exists. The model will look like this, where we have plenty of molecules surrounding each other. So the iodine molecule is the iodine molecule itself is really caged and packed next to each other. So the degree of freedom or the ability to mobilize and move around is very small and almost non-existing. Okay, so that's when it comes to the iodine solid. Okay, so for metallic solid, as far as I'm concerned, the only thing that I would like you to know about this is that the metal solid exists as cations, positively charged, obviously, with a sea of electron that surrounds that positive charge to stabilize the structure. Okay, so it's cations surrounded with sea of electrons, negatively charged, obviously, the electron positively charged the cations, and that's how the solid structure of metals is stabilized. Okay, and it's basically a plane of cations surrounded by these electrons. So I think that brings Unit 3 to conclusion, and that should cover everything for Unit 3.